All right, class. Hello. So today we're going to take a look at titrations, and I also want to go over what they are and how you could do some problems to solve for unknowns using a titration. When you guys are back on campus next week, we will be doing titrations in person. So I think the idea will make a little more sense. But today I want to get you guys acquainted with just the setup of a titration problem and how they work. We're also going to be doing a review of redox reactions, which is complete review from last year. So I don't think there's anything new that you'll be seeing there. So those two topics I want to cover with you guys today. So let's go ahead and get started. So a titration, here's what it is. It's where you use two aqueous solutions, and one of the solutions we know the information about. Like we know the molarity of it, we know how much of it we have. And then we're going to be reacting it with the second aqueous substance. And in this scenario that we're looking at here, for the simple titrations that we're setting up together here, these are for acid-base titrations. And we use acids and bases when we're doing titrations because they neutralize, right? You guys remember an acid and a base, they come together, and then the H plus and the OH negative, they form water. So you get this process of neutralization. But by doing this neutralization, what you could do is you could figure out how much of one thing you need to completely neutralize another thing, right? So we could figure out the point where the moles of hydrogen ions are equal to the moles of hydroxide ions, and that's where we actually stop the titration itself. So if you look over to the right, you could see a setup of what a titration is going to look like. This you're seeing a portion of the burette. We've used this before, right? You guys have flipped it over though, and we kind of made it into a eudiometer to collect gas in our last lab that we did. But in this scenario, we're using it for the function that it was created for, which is to dispense an aqueous substance at a very slow rate, or it could be a fast rate if you guys just turn the nozzle a little bit. Inside this flask, you would be putting in the solution of the thing that it is that we do know. Okay, so whether it's the acid or the base, you're going to be putting it into a little flask. We're also going to throw in an indicator. So the indicator that's really commonly used for neutralization titrations are phenolphthalein. You probably remember it. It turns like a fuchsia, pretty like pink, pinkish purple color in the presence of any base. So it's an indicator to let us know whether we have any base or not inside of our flask over here. And then in this part, the burette, you would fill it with the liquid that you're trying to figure out the concentration of, right? Or you could flip it. It kind of doesn't matter which way you do it. But the key thing is one of them you know everything for, and it's for the other chemical that you're trying to figure out the concentration of it. In titrations, it's a technique that's done all the time. They use it to figure out molarity of unknown acids or bases by just neutralizing it like this. Okay? We'll talk about this equivalence point in a bit more detail on the next slide, but it's the point where you have equal amounts of moles of hydrogen ions and moles of hydroxide ions. So basically they form water, right? And when these points are equal, you don't have any excess of hydrogen or hydroxide, your titration is done. And actually this isn't, you would use one last drop and then you would know that you've reached the equivalence point, the drop prior, right? So that's a more exact way to think about it. But let's go ahead and take a look at this problem here. We're taking sodium hydroxide, right? And we're reacting it with sulfuric acid, H2SO4. I think your notes, it says H2CO3, but you could go ahead and change it to sulfuric acid. So we have strong base, strong acid, right? And we're trying to figure out something about one of our chemicals. And I'm gonna just sum it up here. For sodium hydroxide, I don't know the molarity. That's like my question mark, okay? And we know that all this information about the acid. We use 27.30 mils of it, and the molarity of the acid is given to us. Okay? And we also know here This is how much base was used before they, and this is the point where this is all equal, the equivalent point of moles of hydrogen being equal to moles of hydroxide. Okay, so I'll tell you guys two different ways you could solve this problem. The first one is my preferred method when you're doing a titration with acids and bases. The second method is something I'm going to teach you guys because it's more useful for titrations where it's a little more complicated, like redox, which we're going to look at next week, or titrations where you don't have milliliters of both substances. Like you might be starting off with grams of one of the acids or bases. Like we could easily measure out a grams of sodium hydroxide and then kind of add water to it and go from there. But so this is kind of what we're going to do. Okay, so this is my info, right? And here's my equation. M of A times V of A is equal to MB VB. And you might recognize this equation. We've used a variant of this before as we talked about dilutions, right? And it's because the principles are the same. Molarity times volume would give me moles of acid right here, right? And we're saying this is equal to molarity of base times volume of base, which is equal to moles of hydroxide. And remember, we're stopping our titration at this equivalence point where this is true, or where we think this is true. Okay? So we could use this setup, but there is something in addition that you need to remember over here. The acid itself, right, might not be a monoprotic acid. You guys might have like more than one hydrogen ion inside the acid, like we have in our case right here. So you need to also remember the number of hydrogen ions we have inside of our acid. So that needs to be included. Our case would be 2, right? For the base, we also have to include how many hydroxide ions we have in our base. In our case here, there's 1. Okay, so the reason for that is because this is essentially a shortcut to stoichiometry. The traditional way of doing titration problems like this would just be do a stoich setup, and I'll do that with you guys too. But this is just faster. And we also have to account for the ratio of hydrogen to hydroxide ions. And we do that just by incorporating it really simple, like this. So let's do it. 2 hydrogen ions. The molarity of the acid, 2.31. The volume of the acid is 27.30. The molarity of the base is my unknown. The volume of the base is 18.4 mils. And the number of hydroxides is 1. Okay, so if you went through and you just punched it out, you multiplied and divided by 18.4, the molarity of the base is going to come out to 6.85 moles per liter here. Okay? And this means that our base, right, had a concentration of this much, and we needed 18.4 mils of it to completely neutralize 27 mils of a 2.3 molar acid. And you might be thinking, like, how does this make sense? Because why is the concentration of sodium hydroxide so much higher than the concentration of the sulfuric acid, right? And the rationale for that is this, you guys. There's 1 hydroxide here, whereas we have 2 hydrogen ions here. Right, so we could see that we need like double the amount of NaOH in order to neutralize like 1 molecule of the H2SO4 because there are 2 protons inside H2SO4. So here's our easy way to solve. The more complicated way, which isn't really that complicated because we all know how to do stoichiometry at this point, it just takes a little more time, is to do stoich. And even if you're like, I don't want to, I'm going to skip this part, Mrs. Han, because you said it just takes extra time. I want you to actually write it down in your notes because you're going to have to do problems using stoichiometry for titrations if they do not give you the amounts of stuff in molarity, right? And they might give it to you in grams. Then it makes a lot more sense to use stoichiometry like this. Okay, so here's our balanced chemical equation. I wrote it out before, right? We make water and sodium sulfate, 2:1:2:1 ratio. Now, I'm just gonna walk through the stoich. I know everything about this acid. This base is my unknown, and I wanna calculate molarity from it, okay? This is the part where we finally get to go to the very bottom of the roadmap when we do our typical roadmap stuff. So let me go ahead and write this out. We have 27.30 mils of acid. And I don't want mils, I want moles. All right, so I'm going to do my conversion here. I'm going to divide by 1,000 mils, and I'm going to multiply it by the molarity of the acid. So these cancel. And now we do our switch. I have 1 mole of acid, and I have 2 moles of NaOH. You know this, like the number of hydrogens and number of hydroxides, we essentially did stoichiometry like built in to the setup of this equation earlier. So that's why we were doing that. And then if you guys stopped right here, you would get moles of NaOH, but I want to get molarity of the NaOH. So this is where you guys do that extra step of taking moles and dividing it by liters, right? So we have to take the 18.4, divide it by 1,000 and get 0.0184 liters of NaOH. And then if you guys multiplied and divided all the way through, you should end up with the same answer. Right, so the molarity of the base we find out is 6.85 molarity. Okay. If you have questions here, just go back and rewatch or send me an email and I could answer questions that you guys have for this. Now, you guys could see our setup of our titration, right? You have a flask, we have some sort of an indicator here. The solution that we have in here, we call the titrant, right? And we're gonna add little by little. In this case, if it is already like, so if you're starting off with a fuchsia color with the phenolphthalein showing, you would stop when the thing becomes clear, right? And you could see kind of our setup here and the graph of this titration curve. We will be spending a lot of time on when we get to our acid base unit. So this isn't anything to worry so much about, but the y-axis has pH, right? And this is just telling you what's happening to the pH as we continue to add more and more of the solution inside the burette. The pH is going up, right? Which is telling you that there is a base that we're adding in. So the pH is going up inside here. And the equivalence point on this graph, like this point right here, once you guys reach kind of like that flat vertical point, that straight vertical point, it's that middle part right there that is considered to be the equivalence point where your moles of acid and moles of base are equal to each other. So don't worry about the graph, but it's an intro and you're gonna come back to this when we do our acid base unit for real. Let's get into redox reactions, right? So last year we talked quite a bit about oxidation and reduction, right? And we even spent some time coming up with mnemonics for this. You guys remember Leo goes grr, Leo the line goes grr, and oil rig, right? You guys might still use those to this day to help you remember what redox is. But here's a definition of a redox reaction. It's moving electrons from one reactant, right, to another reactant that has a greater attraction for the electrons. So it's basically looking at it in terms of transferring electrons. So one thing doesn't really want the electrons, another thing really wants it, so bam, you move them, right? And that's a redox reaction. Now, oxidation just means losing electrons. Reduction is a process of gaining electrons, right? And I think last year we talked about the agent deal, right? You don't need to worry about reducing and oxidizing agents for the AP test. You just need to know whether something is getting oxidized or reduced. Right? If you guys want the memory trick, oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. Or Leo, the lion goes grr. Right? The loss of electrons is oxidation, or the gain of electrons is reduction. Whatever suits your fancy. Oxidation numbers is really important for you to understand what is happening during a redox reaction. So let's go over the rules for how to figure out oxidation numbers. First of all pure elements by itself is 0. So like oxygen gas, 0. Copper, 0. Hydrogen, 0. So anything all by itself is always 0. The monatomic ions, the ions that we've learned before, you want to know that column 1 is always +2 and column 2 is +2. Column 1 is +1, column 2 is +2. Group 17, these are your halogens, right? Those guys have a -1 in terms of its oxidation number if it's attached to a metal, right? So if you have something like, let's see, like chlorine being bonded to nitrogen, like NCl3, right? We can't guarantee that the chlorine actually has a -1 charge because it's not bonded to a metal. The exception to this rule is fluoride. Fluoride we know is always -1. Oxygen, here's another one that's important. It will always be -2, right? Except in the case of peroxide. So if you guys are dealing with like hydrogen peroxide, remember the formula for peroxide, right? It's O2 with the -2 charge as a polyatomic ion. So each oxygen is -1 to have an overall charge of -1. The sum of the oxidation numbers, if you're looking at a neutral compound, it'll always come out to 0. If you're dealing with a polyatomic ion, right, that's why knowing charges on these guys are helpful. It is going to be the charge of the ion itself that is going to equal it out to. And let's go ahead and do these 4 examples together. If you kind of remember this from last year, you could even just pause it and just do it on your own. Otherwise, you could just still keep listening to me talking. All right, so chlorine. We know it's -1. There's 3 of them, right? So I know the Fe is going to be +3, right? So I would say that iron has +3 oxidation number. Each chloride ion has a -1, right? Here, the fluoride, -1, right? There are 5 of them. So I know to balance that out and make it add up to 0, the phosphorus here has to be +5. Right, so this is just a really good, clear indicator and example of how for your covalent compounds, your nonmetals that are bonding together, your PF5, like the phosphorus, if you guys find it on the periodic table, it doesn't have a -3 charge as it does in an ionic compound. It's actually holding a +5 oxidation number. Let's do this one. We know the oxygens are always -2. Right, so there are 4 of them here, so they add up to a total of -8. In total, right, the charge has to come out to -1, whereas in these guys, the charges all came out to 0. So to balance that -8, right, and then make it -1, chlorine here has to be +7. Right, so this is another good example of how chlorine, it's not automatically -1. The oxygen we know for sure, but the chlorine you have to figure out by using the other element to know. All right, dichromate. So oxygen, -2, there's 7 of them, so it's a total of -14. We need to make the charge add up to -2, right? So you could see that if this is -14, right, then you might be thinking, oh, chromium should be +12 to make it add up to -2, but there are 2 of them, so it's going to be +6 for each of them, right? So for each chromium atom, we would say that the oxidation number is +6. For each oxygen atom, the oxidation number there will be -2. And I am done for today. If you guys have any questions, please send me an email. And then tomorrow when we see each other in class, we will go over some more topics about redox. And that hopefully should be just review for you guys from what we did last year. All right, bye guys.